Good afternoon, everyone. This is Sadia Zafar from HRAI. I would like to welcome you to today's session on safer indoor environments utilizing hydronic solutions. This session is brought to you by TACO. A presenter, Mike Miller, will discuss available options and compare them to existing buildings with hydronic upgrade solutions and new construction planning in the early stages. Moving on to housekeeping, you will notice on the control panel of your screen the Q&A feature. Please use the Q&A feature to ask your questions at any time during the webinar. They will be addressed at the end of the session. Also note, this webinar is being recorded and the recording will be shared with you following the session. Now we will begin the presentation. Welcome, Mike.
Awesome. Hello, everyone. Thank you so much for joining us for this lunchtime presentation. Great to have you guys on board, and really pleased to be able to share some time with you here for an hour. So again, welcome and thank you. And before I get going, I just want to briefly highlight some of the other up and coming HRAI seminars that are coming up that are readily available on the HRAI's webpage. Lots of great information there to be learned and shared over the next few weeks and months. All right, so let's get into this. So the subject of here says clean air doesn't have to cost more, and it highlights chill beam as a technology that we'll certainly talk about in this presentation, but I want to make sure that it's clear that it's not limited to chill beam. There are several other hydronic options available that can aid in what we're going to be discussing here throughout this hour, and I'll make reference to that throughout this session. So our goal today is to highlight some of the opportunities that can help address some of the challenges that have come into play since the COVID pandemic has hit. We'll walk through some of what some of the experts have been recommending for getting buildings back open and safe, not only to deal with this current pandemic, but also will help make our buildings and indoor environment safer for any other airborne sort of transmission of any kind. Okay, so moving on. So one of the things we'll go through at the beginning here is we'll walk through of what some of the experts have been recommending for those buildings to become safer. And that's here we make reference to work and school places, but it's really true for any indoor environment for that matter. We'll look at improving the indoor air quality, again reviewing what the experts have been saying and recommending, and then also we'll look at some whole total system solutions and an example. So who are the experts first and foremost? All of those are definitely, I'm sure, a household name for all of us, at least by now. ASHRAE always has been, of course, but then we all learned a bit more about the Centers for Disease Control in the US, and also the Environmental Protection Agency, or here in Canada, NRCan. But let's quickly look back in time. This is not the first pandemic that we faced in the last 100 or so years, actually just a little bit more than that. We had the Spanish flu between 1918 and 1919. During that time, buildings changed to deal with that pandemic at the time. It became very evident that we needed to increase the level of ventilation that went into those buildings. So in those days, buildings completely were opened up and a lot of more fresh air was introduced to the buildings. But just like anything in time, once you get over a certain challenge, after a bit of time has passed, we tend to forget about things. So we all became comfortable again. And then as time progressed, we started looking at other things that were important for us to look after indoor environment. For example, air conditioning. So when air conditioning was introduced, buildings became more enclosed, and ventilation was introduced through the HVAC system. And then, of course, as time went on, energy management became another issue, and focus in design, and then the operation of the building as a whole. So in those days, to lower the energy costs, ventilation rates were reduced to recommended levels between 12 to 17 CFM per person, depending on the building use. That's until now COVID hit us. Today, the CDC, ASHRAE, EPA, and even the World Health Organization or our own NRCan come forward with some additional recommendations that they're talking about. Not much has been really, to my knowledge, today put in writing, but it continues to be discussed, and moving forward, we seem to have a good handle on where we might need to go with those buildings. This slide is something that I was provided with by a very good friend of mine, Robert Bean, who's one of the leading thought leaders and one of my mentors in the industry, that can talk an awful lot more than I could about creating safer indoor environments. This is the slide that he's allowed me to share. Basically looking at some of the key elements that we've all put in place over the last couple of years to try and deal with this pandemic. Obviously, vaccination was one of them. Then we talking about indoor environments. We want to clean the air when possible, if not, or also include wearing N95 masks where equal. We want to defend our personal space with minimum distances that were discussed. And then also, of course, looking at indoor spaces again, looking at the leading associations like ASHRAE as an example to make recommendations on the ventilation piece and guidelines. Air filtration is another thing that we talk about a little bit more these days, and then also controlling the relative humidity going into the spaces as well. Anyway, this is pretty high level, very nice slide that I thought I'd implement here. Here's a statement that was made by the World Health Organization that I wanted to capture for this presentation as well. They said, our findings indicate that building operation practices such as ventilation, filtration, and humidification substantially reduce the environmental aerosol viral load and therefore inhalation dose, and should be prioritized to improve building and health safety. COVID is airborne. But again, very relevant topic today, but certainly there's other viruses and whatnot that might be airborne that can be addressed with any kind of building solution we come up with today. So fast forwarding a little bit, there's several recommendations, of course, that have been made, but the four that stand out to us that we can address with our field, with HVAC systems, as a matter, they'll include dilute, exhaust, containing in the air. Containing and cleaning the air. So diluting means increase the ventilation, which discussions have been had around raising outdoor air requirements, perhaps from 17 to 34 CFM, so effectively doubling it. Simply stated, introducing more fresh air into the building to displace the pathogen-laden air. And then exhausting. Exhaust represents we want to remove some of the pathogen-laden air by exhausting from the building with fans. Could be as simple as opening windows in some cases, but if you do it, if you can do it mechanically, we can control it. And then number three, contain, which means maintaining a relative humidity level between 40 and 60%, which creates an environment where bacteria and viruses are limited in both the survival rate and the ability to spread. And then the fourth point is cleaning, which COVID-laden particle sizes are between 0.5 and 1.5 microns. MERV 13 filters remove about 85% of particles in this range. A MERV 14 filter would remove 90% or higher. So those are some of the things that have been considered. There's other suggestions that have been made to help with indoor air quality that involve bipolar ionization and the use of UV lights to kill the virus. While those might be applicable in some cases, some of the challenges associated with those is potentially air velocity, meaning that the air can be moving too quick to effectively kill the virus. Since the initial recommendations have been released, additional updates have come out and recommendations have been made to minimize air velocity whenever possible to avoid cross-contamination to occupants in the same space. That's a very big one. If you can eliminate return air, that will be a great help. So again, let's talk real quick about what is known about this particular virus, particles. The virus on its own, again, is 0.1 micron or smaller. The lifespan on its own is very short, in many cases less than a minute. But when attached to molecules such as water or saliva or humidity, for that matter, it can last longer, sometimes days. So when we look at the recommendations that are all can play a role in mitigation, we can quickly identify some that are better than others that we can address with our trade in our industry. So diluting the air and exhausting would by far represent the greatest impact that we can provide. When you think about containment filters today, we don't know at this time the potential hazards associated with it. But again, minimizing the number of locations for those will help us address those a little bit better in the future. Now, this page is an active link. I believe we are making this PowerPoint available for sharing purposes. If we are, if not, anybody can contact me at any time. This particular slide here shows a link that takes you straight to ASHRAE, a great landing page where there is a lot of other additional technical resources available that kind of support this particular topic. Feel free to reach out to me and if you want to get your hands on that. Okay, so at TACO, we like to take a whole system solution approach. So many of the items that were listed by the expert to mitigate the spread of the virus are inherent to chilled beam systems, but not limited to. So let's start with indoor air quality. So to improve indoor air quality, the very first thing we can do is eliminate return air. So if there is no return air, that means all air introduced to the building is via a dedicated outdoor air system in this particular site. I'll cover that a little bit more in detail moving forward. But if we can eliminate return air, that means we can eliminate the chance for cross contamination from one space to the next. And again, the following slides will make that a little bit more clear. Also, low velocity. That's a big point. So if we can minimize the amount of air turbulence that there is in a space, again, it'll minimize the amount of particles can be blown around and then spread from one individual to another, I suppose. So looking at heat emitters that provide low velocity will certainly help make buildings more safer. So an example for that could be chilled beams, and we'll look at some examples of that in the coming slides again. So there's active chilled beams that can that tie into the ventilation system, but they'll also be able to provide heating and cooling means. Again, more on that coming up in the following slides. But also other types of heat emitters, as an example, radiant floor, radiant ceilings, radiators, and so on and so forth, can reduce the amount of air that is being blown within a particular space to in order to minimize some of the cross contamination that could occur otherwise. Now we're also talking about proper room humidity control. Proper control of the space and its condition can ensure proper humidity levels. Looking at the chilled beams again, we'll talk about how we can control the humidity levels to the space. Again, to help in the process of making safer indoor environments. A big part, though, however, is the no cross-contamination of zones. So because in this example we'll cover through, we'll look at eliminating return air as much as possible, which will already minimize the amount of cross-contamination from one room or zone or classroom to another. Some of these things we'll talk about also include some reduced maintenance components that will come out, less equipment, for example. Single pipe systems uses the example we're going through later, will use wet rotor circulators and whatnot for the distribution of the energy. Also, less filters could be used in this particular system example as we go through it, because in this case the filters are located in a dedicated outdoor air system. We also want to look at reducing the airflow again as a whole. The system example we're going through today can reduce the airflow by as much as 70%, which some of the side benefits, apart from the cross-contaminating piece or the elimination thereof, some of the other benefits include that it's reduced air noise. Chilled beams, as we go through it, will operate on low velocity air, thus the air movement is virtually undetected. Also, we'll look at the lower energy cost. As we're going through the system example, you'll see some of the points we'll make. that we can overall reduce the energy costs associated with the distribution of the energy. If we do it through hydronic means versus air only, we can come up with some savings there, which are primarily in the savings coming from the fan horsepower needed for the building. Also space savings. Again, we'll touch on that subject a little bit, but looking at some of the types of options we'll have available by delivering the energy, the BTUs via hydronics versus air, generally allows us to supply the air throughout the building with a smaller duct size and whatnot. That's where the space savings could come from. Now, we understand that there are some challenges upgrading some existing buildings to a solution as such, but we'll cover them and still be able to provide that safer space without increasing the operating costs. But there are significant savings that can be realized if a new building is designed already with a hydronic means, just by controlling some of the upfront costs. So, for example, we can reduce the overall ceiling space, which can reduce the building height, or perhaps allows us to add another floor to a larger buildings. By the savings we'll save from the ductwork. And also we can reduce the airflow, which there are significant savings in electrical gear as well as mechanical equipment. So let's just go through that a little bit more. Let's look at the chill beams. Of course, there is different types of chill beams available. There are active and passive chill beams. So what we're focusing on today is a active chill beam, which basically what it represents is it has a fresh air duct ducted to the chill beam itself, which is providing the ventilation needs for this particular zone. And then there's also a heat exchanger on the inside that we can deliver with warm water for heating, or cooled water or chilled water for cooling needs. But in any case, the chill beams operate with water or hydronics and not with refrigerant. Again, just focusing on the active chill beam part because it does incorporate the ventilation piece. For passive chill beams, they still work as well for heating and for cooling needs, but we still need to worry about the ventilation piece. And then we're going to a heating or cooling piece of equipment without the ventilation only. Again, this is where we would consider additional types of hydronic heat emitters, whether those be radiant floors, radiant ceilings, radiators, and whatnot. So let's look at the particular building. When you look at the cooling load in a space, and again, it's not always like that, but more often than not, it is split with 70% of the load being sensible load and 30% being the latent load. The latent load is typically the humidity in the space that has to be removed, and it can come from occupants, infiltration, and in poorly controlled systems be introduced with the outdoor air. So with an asterisk, we'll talk about how we do that in this particular example in a little bit. Now, the sensible load, as you all are aware, is what raises the thermostat up and down. It comes from the infiltration, like latent as well, with people, computers, and other things in a space that emit the heat. So most systems today are designed to handle both sensible and the latent loads in one piece of equipment, whether it's the air handling unit, the fan control unit, package unit, etc. Now, with the chill beam systems, we physically want to decouple the latent load and the sensible load. This is the core design principle that drives tremendous operating savings within an active chill beam system. So the latent load in this example would be handled with a dedicated outdoor air system, short DOAS, and the sensible load is handled in the space by the active chill beam. So as I noted just a couple of seconds ago, the sensible load is typically about 70% of the total heating load. And guess what? There's little to no fan power needed to handle the sensible load with a chill beam system, because the significant energy savings are coming by not having the horsepower associated with about 70% of the cooling load. Again, more examples coming up that'll further clarify this. Now, this slide I won't spend an awful lot of time on, but I'm sure most of you are aware that here's an example. If we were to move 1 ton of sensible cooling with 12,000 BTUs an hour. Through a air duct, it would require about a 10 by 12 inch duct size. Doing it with hydronic means that same amount of energy can be delivered in a 3/4 inch tube, if you so will, and less than 2.5 gallons per minute. Hence, that's where some of the savings will come from down the road. Now let's look more into the physical chill beam itself and how that works. So here's an active chill beam example, a nice little sketch of it. So the fresh air, the ventilation piece, would be ducted to the opening of that chill beam. That's where the fresh air is introduced. And here's an example given where we need 400 CFM of airflow as an example. 100 CFM of fresh air ventilation is introduced into that chamber of that active chill beam. Within that chill beam, there's a couple of nozzles on either side, smaller openings basically, that the fresh air is being forced through. And as the air is pushed and forced through that opening or orifice, if you will, it'll increase the amount of velocity slightly. So it's forcing it through there. That 200 CFM that now exits that that 100 CFM of fresh air coming in that's being forced down through those nozzles will actually induce the warmer space air from inside the space and run it across the heat exchanger. So if you're running warm water through here, it's creating the heating mixing here, where you can actually increase the air temperature. And in cooling means, or cooling mode, you would run chilled water through here, so the warmer room air will pass that heat exchanger and then mix with the fresh air, and then it's effectively cooling down the air into the space. So we're only using, in this case, 100 CFM of fresh air mixed with 300 CFM of the existing space air in the space. It mixes and it redistributes at that 400 CFM throughout the space. All right. So how does that impact the space itself? So on the previous slide, noted that the cooling was delivered by low velocity air, and highlighted from the expert that low air velocity is important in minimizing the spread. So the graphic on the left in this picture here is from a test lab space that shows the path of the air coming from a chill beam. So you see the fresh air entering the top of the chill beam here, and then here's the distribution within the space. So what you're seeing here is a Coanda effect, where because the air velocity is low, the airstream hugs the surfaces, or in this case, the ceiling and the walls, and then falls through the space as shown by the image on the right. So on the right, we show that the temperature gradient in the same space conditioned by a chill beam. In this case, most of the delta T in the space is at the vents of the chill beam. The rest of the space is a very homogeneous temperature throughout this occupied space. In this case, we are able to provide comfort without noticeable air movement. So looking at the chill beam and how it offers a decoupled system, here we show an example of a dedicated outdoor air system. The outdoor air is, in this case, conditioned to treat the latent load. And it's basically any of the fresh air that's coming in from the outside is being conditioned right here. So here's where we might have your MERV 13 or MERV 14 filter. If it's cold air coming in, we have a preheat coil here. If the humidity needs to be controlled or cooled, we have a cooling coil here that can help us control that, and then a reheat coil if needed to increase the temperature of that again. And then we have a small fan, or a fan in this case, that would distribute the air to the building. When we talk about operating chill beams, again, we're talking about surfaces that are exposed within a warmer space. When you introduce cooled or chilled water to it, condensation could become a challenge. That is one of the primary things that we need to consider when we use an active chilled beam system as an example, and we'll address how we can solve that potential challenge. So first, I guess, before I even get there, first I want to make sure that it's understood that in this case, whatever the humidity level is that comes in from the outdoor air, if it's super high, like it might be the case here in Ontario as an example, where we have north of the 90% humidity level. So as we introduce that fresh air into that building itself, it's captured right at the DOAS system and will dehumidify into that 40 to 60% range. So it's already compressed. So the air that we circulate throughout the building is already treated for humidity first and foremost. And then we'll further address it on a zone level in the room by the active chill beam. But in order to achieve that, what we need is a control system that can operate that. Again, there'll be a slide coming up down the road. So in conventional systems, for example, such as VAV, the latent and the sensible loads are typically handled by treating the air in the air handler and then distributing it throughout the system. In a conventional chilled beam system, we can often have two systems, a low temperature and a high temperature system, which effectively can represent the latent and the sensible loads. This little sketch example here shows the low temperature system that would handle the latent load, which operates typically in very low fluid temperatures. Here we show a range of 42 to 52 F. Average or mean temperature often is in the 45-degree range. So in a conventional chilled beam system, you would still have a requirement where that lower fluid temperature is what you make available to the highest load, in this case, looking up into 70% of the load to the dedicated outdoor air system, so it can remove the most amount of humidity there. There are going to be other zones within the building that have high amount of filtration, infiltration, let's say, like I'm thinking of other entrances. If it's a commercial structure, those could be overhead doors and whatnot. But essentially areas where a lot of fresh outdoor air could be introduced with different levels of humidity. In those, typically you want to tend to with fan coils that also operate on that same temperature range. Then active chilled beams typically would operate at much warmer cooling temperatures when used for cooling, typically in the range of 58 to 62 Fahrenheit. So many systems are designed where you have a low temperature system that looks after the DOAS and other high infiltration areas, and then a lower temperature cooling system utilized for larger surfaces like active chill beams, but also if you're talking radiant floor walls, radiant floor ceilings and floors, you would be more likely to operate in that range. So this example shows a second system that is used for the cooling. So we have a low temperature cooling and a medium or higher temperature cooling system, if you so will, that might even operate at tighter delta T. You can use different equipment that's more efficient at smaller delta T's for this application versus the high infiltration zones, I suppose, or terminal units could possibly run on a larger delta T. So here's what a system example could look like if those were addressed as two separate systems. Again, your low temperature chiller and your high temperature chiller system. In many cases, they're supplied with supply and return. So we already got a 4-pipe system just looking at the cooling. Now, if you were to add a heating loop to all this, those could be 6-pipe distribution systems. Effective, will work, but in our opinion, there's a way to further minimize the total operating costs and installation costs. In this sort of arrangement, typically you have larger pumps in a mechanical room, and then you would use some sort of two-way control valves at each of the terminal units to get the flow only to where you want it, and perhaps some bouncing valves that will tweak the bouncing through that terminal unit as well. Now, what we would like to propose is a solution that encompasses all of that with quite a fewer pieces of equipment and components and less pipe, and therefore also resultant less labor savings. Again, any of those options will work. This is just one we want to focus on here. So in this case, we'll show a low temperature chiller in this case that would now be operating on a potentially much larger delta T, so that will help its operating efficiency. But now we would focus on having a one pipe distribution system throughout the whole building. So instead of 4 pipes before for heating and cooling, now we only got one that goes around the building. What you would like to do or want to do ideally is to have the higher requirement or the higher loads to come off that loop first, so they can truly see the lowest possible fluid temperature available. So absolutely, the first load should always be the DOAS system, which is your biggest load in the building. And then off that primary loop, you could then come up with any of the other terminal units or heat emitters. But again, I would like to encourage you to keep some of the higher infiltration zones or terminal units at the lower possible temperature. In a one pipe distribution system, of course, it's I'll talk about this a little bit more in detail. But of course, as you see, as we take multiple loads off every time you take off a load from a one pipe distribution system, the second load would see a slightly higher supply temperature in the primary loop. And here's why. So there's one pump in this example that circulates the water through this loop. At each of these zones, there is a form of hydraulic isolation, which is right here. Those are a hydraulic separator that could be achieved through perhaps two closely spaced T's. That gives you that hydraulic isolation, or there are engineered fittings available that essentially achieve the same thing, but with fewer connections. And then running that lower fluid temperature throughout the building to deal with some of the condensation challenges that you might be faced with. We would install some form of mixing that can control the water temperature provided to the terminal unit. What we'll focus on the next slide is showing you an example how we can do that with injection pumps. But before I even go there, I just want to mention this is just one example that we want to show here. The same mixing can be achieved with using three-way or four-way modulating or floating type mixing valves. It's coming down to the control strategy that will achieve that. But again, we're talking about any particular mixing device in general. So here's an example of what, oops, I need to get rid of my beautiful scratches here. This is an assembly that we offer through TACO. Again, this is just one option, but in this case, you'd have your one pipe primary distribution system here, your form of hydraulic isolation that'll go into a variable speed mixing pump. In this case, so that's a pump that can be controlled by changing the frequency of the voltage. In our case, we'll control the speed of it with a 0 to 10 volt modulation signal. And then what you're looking at here, that's a hydraulic separation piece. We call it the H mixing block. So that achieves hydraulic separation, but also it becomes the mixing chamber right within here of the fluid temperature. So again, if the cold water comes here in the 40-degree range, but we only want to send 65 or something like that, or north of 60-degree Fahrenheit water through the active chill beam, then we'll control the speed of this pump to control this discharge temperature going to the terminal unit. So this becomes a constant speed zone pump, and this is your injection pump. Hopefully that makes sense. If not, you're always more than welcome to ask questions now or later. So the control system is what really becomes the crucial part of this to avoid condensation in this area here on the surface of the chill beam, so it avoids the rating in the space. So the controller employed here. So what we'll do usually, here's some of the key things, I guess, to consider. We want to look at all the conditions of the air coming in from the DOAS system. So whatever the fresh air is being provided through the chill beam, as we mentioned earlier, it's already pre-treated by the DOA system. So it's already in a range that we only need to adjust it slightly to control the humidity further down to the zone level or the zone requirement. Is it the proper temperature, for example, or is the air dry enough, or are there any other issues detected with the supply air coming from the DOA system? But assuming everything is fine, we'll continue to operate this chilled beam zone. Next, we would look at the space condition. What is the temperature and the dew point in the space? Then we look at the fluid temperature that is provided to the chilled beam. Assuming we have safe conditions to operate, the system ensures just enough chilled water makes it through the active chilled beam to provide proper cooling to the space. But this can't just be a one-time thing. It needs to continually monitor these conditions and make changes to it as necessary. If the dew point in the space changes, we have the ability to track up or down the supply temperature provided to the active chilled beam in order to ensure we do have condensation. We don't have condensation developed in the chilled beam. If the conditions are not conducive to the operation, in this particular case, this control system or any control system in its place should be able to alarm and shut the operations down for this particular space to avoid that condensation piece. But again, a controller that has the inputs and outputs to control the variable speed pump, the secondary pump, has the ability to see space temperature and humidity, but also control to a delta T that you want to maintain within the space. All right. So here's what a system example could look like. Again, we have the DOA system, a control system that comes perhaps even with some sort of graphical interface for monitoring and troubleshooting purposes. But the controller itself should be able to control what happens to the fluid temperature provided to the thermal units, what the space is doing, and to control the space comfort level as well. And then also perhaps any of the mechanical devices that might need to be controlled. So let's look first and see how we can achieve some operating savings going from, let's say, a traditional VAV system, if you so will, to a hydronically adjusted heating and cooling system. Just focusing first, the first thing that's get off the table, whatever the building load is, heating or cooling, the generation equipment typically consumes the same amount of energy. The load is what the load is. But where can we save some energy from? In this particular case, it comes in how we deliver the BTUs from A to B. In the traditional VAV system, you'll see that there's some distribution energy, but then the biggest part of that energy here is captured by the fan horsepower that's required in order to deliver that total air volume for the building through it. When we go to a hydronic system, we can reduce the amount of air that's being blown throughout the building, because in this example we're covering today, we're looking at only delivering the ventilation piece of air to the space. So that allows us to reduce the overall fan horsepower significantly just to that of the ventilation requirement. And then what you would see in the middle here would be a traditional 4 or 6 pipe chilled beam distribution system, where you might have 3 different distribution loop temperatures, 2 for cooling, 1 for heating. You would have 3 pumps, and then you have all those balancing valves and zone valves in place. If we compare a traditional hydronic chilled beam system to what we would refer to as a injection pumping or load match low flow chilled beam system, that's where we have a 1 pipe distribution system for heating, running the heated water through the building, and then a 1 pipe distribution system for the cooling or chilled water system. And then we have those individual different mixing devices throughout the space. That allows us to reduce the operating costs quite a bit more. So just by going from a traditional VAV system, and again, this is a very broad statement, and of course it changes from system to system, but it's not uncommon to see energy savings in the neighborhood of 22 to 25% range just by converting it into a hydronic means. And the savings can be significantly more between 30 and 35, maybe even greater than that, energy savings by combining hydronic with a one pipe distribution system. Now let's look at some building examples. But first, before we get into it, there are always several design conditions that we have to keep in mind. The DOAS system, the sizing of it has to be done for the largest of loads. It handles the latent load. Oops, I still get those marks on my screen. Apologize. Again, we want to consider the use of fan coil units or other equipment around entrances that have high times or high latent loads. So again, high infiltration areas. And we want to control the chilled water to chilled beams as an example to be within 5 degrees above the space dew point. And if possible, we want to design the chilled beam to stay within 4 to 5 degree delta T, where the overall building loop, its delta T could vary by as much as 14 to 16 degree. Consider the single pipe injection pumping system to maximize the energy savings. So now looking at a particular building example. This here happens to be a 5-floor office building, 200,000 square feet. In this instance, 400 square feet per ton, to a total of 500 tons. The annual operating cost of this system, currently heated and cooled with a VAV system, runs at about $360,000 per year, based on these operating costs. Again, this is just a particular example. Here's what the system would look like. In this case, we're working off that 17 CFM per person ventilation rate, which equates to about 10% of the total airflow requirement in this particular building. So the building, in this case, again, it needs 200,000 CFM of air supplied to it. This particular example here utilized a fan that's 210 horsepower to distribute that air throughout the building. Now, if we're only bringing in 10% or 20 CFM of fresh air into the space, this would be the same amount of air that we would exhaust, meaning everything else that we're not exhausting would, in this current state, be a return air scenario. So again, 90% of the air that is just coming back from the building that may potentially be contaminant laden. And now we're returning it back through the building. And I guess what is physically possible is that we've now taken air from a space that was completely safe, but now we're mixing it with air that could have come from a compromised classroom or office space, and then we remix it and introduce it to the rest of the building. Even here in this example, still utilizing a 40 horsepower return air fan. So how can we make this building a little safer? Well, as we discussed, double the ventilation. So here we're taking now the requirement from 17 to 34 CFM per person. That same size building, same load now typically would run to about slightly different load because we're introducing much more fresh air. Now we're looking at 300 square foot per ton, total of 667 tons of cooling now required. The operating costs now increased to $440,000. So that's an $80,000 increase. The system itself again looks the same, except for now we're bringing in the double amount of fresh air. So now we're bringing in 40,000 CFM. We still have the same size fan that still moves the same amount of air throughout the building. And as we're returning that air again, and we're exhausting that 40,000, we're now bypassing or returning only 80% of that air. So it's made it better, but we're still potentially cross-contaminating one zone from another. I'm sure there's other ways you can control this. Perhaps you can put some form of additional filters in here, like some of those we discussed earlier on. However, if you can eliminate return air as a whole, we'll make it even better. So the increase of the operating costs really are in this case tied to the increase of the amount of fresh air we're bringing in. and the added load as a result of that. So if we look at this same building example now and apply a one pipe load match and low flow active chilled beam system to it at that same 34 CFM per person of ventilation, the operating costs, as mentioned earlier, by reduction in the overall horsepower, whatnot, are now dropping to $350,000 a year. So there's $90,000 a year in annual savings from a traditional VAV system that has now double the amount of ventilation to a, in this example, one pipe low flow hydronic chill beam system. And here's why. So of course, first we're using now only the DOAS's only job now is to provide the amount of fresh air ventilation that's needed for the building. And as we discovered earlier, at that 34 CFM, we're looking at 40,000 CFM of fresh air supplied to the building. Now, remember that the ductwork in that existing building was earlier sized for 200,000 CFM. We can now get away with significant lower total fan horsepower to distribute the only 40,000 CFM required for the building through that ductwork that's effectively sized for 200,000 CFM. That's why that fan horsepower here is so small. And that's where the majority of those savings come from in terms of operating costs. So now just that 40,000 CFM of fresh air is now being treated. That's what's being filtered coming in from the outside. There could still be some return air recovery by having a runaround loop that essentially has a heat exchanger in the exhaust fan or the exhaust air panel and distributed to a heat exchanger in the DOAS system to recapture some of that energy. You still have your heating coil, your cooling coil in here, and another reheat coil if needed, and then a significantly smaller fan again to distribute that ventilation piece through the space. Again, remembering that 70% of that building's load is now captured here at the DOAS system, and the other 30% of the heating and the cooling load is now covered by the local zone active chill beam system. I gotta get rid of these scratches I put on the screen for you. So again, the chill beam option, again, in quick summary, we can increase or double the ventilation. We can offset the increased load and cost associated with the load. And we can more efficiently move the BTUs through the hydronic means. We, as well as any of our partners, have all the tools available that can help you look at system examples and help you design them. We have a design tool that allows us to lay out active heating and cooling system through a CAD type drawing program. We have a system efficiency tool that can compare quickly on a very high level different types of operating costs, service costs, maintenance costs for the different types of heating systems that are known to man. We have a load tool that can help, we can use to establish the heating and the cooling loads. And we can also provide, offer some equipment selections and as metal packages. But again, the biggest amount of savings, again, will come from the reduction of the overall fan horsepower, because now we're delivering just a ventilation piece, and all the remaining BTUs and energy is delivered through hydronic means. In a one-pipe distribution system, we now only have a single cooling pump that circulates the water through the space. That's a larger one. Through the hydraulic separation, that pump is typically quite a bit smaller than what would be the case if there was a two-pipe distribution system where there's a supply and a return, because then that pump would also have to carry the burden of the resistance through all the terminals or the terminal units furthest away from the mechanical room. In this case, being decoupled, that pump really just needs to overcome the head of the distribution loop. And then the local zones are being serviced through zone pumps in this particular case, and a one pipe system, but could still be zone valves if it's a two pipe distribution system. Again, a quick summary on this. There are several ways to retrofit existing buildings. So again, if this was a traditional VAV system, we can do what we shown in the example earlier. We can replace this or convert this into a dedicated outdoor air system, eliminate the return air as a whole, and we can greatly reduce the overall fan if all we have to deliver from here on out is the ventilation piece and not the total amount of the 200,000 CFM. Yeah, that's pretty much it, where it's all coming from. The active chill beams, of course, would be down in the zone. Even if converting the building to active chill beams is not an option, and the building has already been heated and cooled with a VAV system, there are some VAV retrofit boxes available, such as is shown in this example, that are providing a similar performance. Again, the fresh air ventilation would be piped to those, and then there's a hydronic coil there that you can still supply with hydronic heated or cooled water, whether it's heating or cooling mode. And there often is a little fan inside as well that you can switch on and off to add some additional fan power if needed on that local space. So chill beam, DOAS systems replacement, or DOAS system with those VAV box replacements is what can help us achieve the reduction of operating costs while increasing the ventilation in spaces to make them safer indoor environments today. That was all, Sadia, and the team that I had to cover here today. Again, I want to thank you just for bearing with me for this short hour during the lunchtime. But I wonder if are there any additional questions that you might have. If not, I see Sadia shared my contact details in the chat. Feel free to reach out to me at any time. Always happy to talk to everybody. The only calls that I regret are the ones that I don't get. So thank you so much.
Okay, great. Thank you, Mike. Yes, I have put in your contact information. So this ends our presentation for today. I hope our members found this informative. If you have any questions, please feel free to reach out to HRAI or to Mike directly. Additionally, please complete the evaluation survey that will appear on your screen at the end of the webinar. And with that, have a great afternoon, everyone. And thanks again, Mike.
Well, one more thing before we forget. We have a very big trade show coming up in Toronto next month. It'll be our first in Ontario since the beginning of the pandemic. Already attended one in Canada early in the year, which was in Vancouver, Cyflex West. Look forward to seeing anybody at the show. By all means, please come see us at our booth or the folks at the HRAI booth. We look forward to seeing you again in person. Thank you.
Thank you. Okay, bye, everyone.